Chapter 1. What counts as a threat? Most rocks that hit Earth are dust to pebble size and burn up as harmless shooting stars. A few are big enough to flash like a camera pointed at the sky. Those are bolides. On February 15, 2013, one about 18 to 20 meters wide exploded high over Chelyabinsk, Russia, with the energy of roughly 500 kilotons of TNT. That's 30 times Hiroshima. Yet still an airburst that didn't make a crater. Nearly 1,500 people were injured by shattered glass. Events like this remind us that even small space rocks can matter locally. Scientists use two labels you'll hear throughout this film. NEA, Near-Earth Asteroid, follows an orbit that brings it close to Earth's orbit. PHA, Potentially Hazardous Asteroid, a subset of NEAs that are both large, typically greater than or equal to 140 meters, and can approach within 0.05 astronomical units, approximately 19.5 lunar distances. PHAs are watched because they could cause regional damage if they ever actually lined up to hit us. Key context. We've found over 90% of the 1-kilometer class objects, and survey teams are now focused on the 140-meter crowd and below. Chapter 2. How Risk is Measured. Torino and Palermo. If you hear about an asteroid with a chance to hit Earth, you need two scales to make sense of that headline. Torino scale, 0 to 10. A simple public-facing color scale. Most objects score 0. A 1 means normal, very likely to be downgraded with new data. Ratings above 3 are rare and short-lived. Palermo scale, logarithmic, used by specialists. 0 means equal to background risk. Negative numbers mean less risky than the background. Values between -2 and 0 are monitored. Positive values would be extraordinary. NASA's Sentry and ESA's NEOCC constantly recompute these as new images pin down the orbit. Objects jump onto the risk lists easily when first discovered, then usually fall back to 0 as the uncertainties shrink. Always check the current tables. Chapter 3. The Watch List. Real objects people ask about. Narration. Here are the names you'll hear most often, what we actually know today. Apophis, 99,942. Famous because on April 13, 2029, it will skim safely past at approximately 32,000 kilometers from Earth's surface, inside the ring of geostationary satellites. There is no impact risk in 2029 or for many decades after. It's a scientific bonanza, not a doomsday event. NASA will even send OSIRIS-APEX to study how the flyby changes Apophis's surface and spin. Bennu, 101955. Target of NASA's OSIRIS-REx sample mission. With improved tracking, Bennu's total chance of impact through the year 2300 is about 1 in 1,750, 0.057%. With the single most notable date, September 24, 2182, at approximately 1 in 2,700. Still very small. 1950 DA, 29,075. A 1-kilometer class asteroid famous for a far future possibility near the year 2880. Updated analyses put its probability around 1 in 30,000, much lower than early estimates. It remains a top technical interest case purely because of size. 2010 RF-12, a tiny rock, approximately 7 meters. For 2095, some solutions once gave a roughly 1 in 10 chance of an atmospheric entry. But even if it did, it would be a Chelyabinsk-scale fireball, not a global hazard. Risk assessments for small objects like this swing widely and get revised with new observations. 2024 YR4. In January through February 2025, it briefly reached Torino 3 for a hypothetical December 22, 2032 impact, triggering intensive follow-up. As more data came in, the risk plunged back to Torino 0, and the 2032 Earth impact scenario was ruled out. It's a textbook example of early risk is not final risk. Chapter 4: Surprise Flybys and What They Teach Us. Narration. On July 25, 2019, asteroid 2019 OK, roughly 60 to 130 meters per second, slipped by at about 65,000 kilometers. It was noticed late because it approached from a tricky angle. No threat, just a wake-up call that we need better sky coverage, especially for objects coming from the sun's direction. This is why upcoming and specialized surveys matter. Ground telescopes work hard every clear night, but some directions and twilight angles are tough. Space-based infrared telescopes can see warm, dark rocks that reflect little sunlight. Chapter 5: If One Hit. Airbursts versus craters. Impact outcome depends mainly on size, speed, angle, and strength. Approximately 10 to 20 meters. Likely an airburst like Chelyabinsk. Window damage over tens of kilometers. Few or no fragments reaching the ground. Approximately 50 to 140 meters. Possible city to regional damage if over land. Over ocean, hazardous airburst in waves near the coast. Greater than 140 meters? The PHA regime, rare, but planning focuses here to avoid regional catastrophe. Kilometer class. Global climate effects. But we've already found most of these giants. Crucially, probability and consequence are different axes. The big events are extraordinarily rare, but non-zero, hence the measured, layered defense you'll see next. Chapter 6: The People and Machines Watching the Sky. Narration. NASA's Planetary Defense Coordination Office, PDCO, organizes U.S. efforts to find, track, assess, and communicate asteroid threats, working with partners worldwide. Surveys like Pan-STARRS, Catalina, Atlas, and many others feed observations to the Minor Planet Center. Risk analysts at NASA's CNEOS, Sentry, and ESA's NEOCC evaluate the numbers daily. In 2023, the U.S. released an updated National Planetary Defense Strategy and Action Plan, a playbook for detection, characterization, mitigation, decision-making, and international coordination. Chapter 7: Practice Makes Possible. DART and Hera. Narration. In 2022, NASA's DART spacecraft slammed into Dimorphos, a moonlet of asteroid Didymos. The result? Dimorphos's orbital period shortened by approximately 33 minutes. The first proven test that a kinetic impact can nudge an asteroid. ESA's Hera launched in 2024 and is on course to arrive in late 2026 to measure the crater, internal structure, and momentum transfer precisely, turning the demo into engineering data. This wasn't about a dangerous target. It was about learning how to do deflection with years of warning. Chapter 8: Finding the Ones We Still Miss. NEO-Surveyor. Narration. To catch the tough, dark objects that sneak in from the sunward side, NASA is building NEO-Surveyor, a dedicated space telescope in infrared. It's designed to accelerate discovery of the greater than or equal to 140-meter population and improve warning times. Current plans target a late 2027 to 2028 launch window. The goal isn't to scare anyone. It's to turn the unknowns into knowns while we still have decades to act. Chapter 9: What happens if an asteroid scores greater than 0? When a new discovery lands on the Sentry or NEOCC risk table with Torino 1+, observers worldwide jump in to reduce the uncertainty. Most cases drop to 0 within days or weeks, as with 2023D W in 2023 and 2024 YR4 in 2025. If a non-zero risk persisted years ahead, agencies would rapidly characterize size, shape, mass, spin, composition. Model the trajectory and how it responds to deflection. Decide on mitigation, e.g. kinetic impactor, and launch windows. Coordinate with international partners per the 2023 strategy. Chapter 10. The Next Decades. Cautious Confidence. Narration. Here's the bottom line. We discover new near-Earth asteroids every week. The vast majority will never threaten us. A handful will temporarily look worrisome until better data says otherwise. The big problems, the kilometer-class objects, are largely cataloged. The mid-size PHAs are the focus of the coming decade, with space-based surveys to close the gaps. If a serious object ever does line up, DART/HERA shows we can change an asteroid's path, if we know early enough. The smart posture is neither panic nor complacency. It's steady investment in finding, tracking, and, when needed, nudging.